Good afternoon and welcome to today's presentation, Pollution Prevention Opportunities in the Metal Finishing Sector. I'm Olivia Newport, a webinar support contractor to the U.S. Environmental Protection Agency. Before we get started, let's review a few housekeeping items. Audio is available for this presentation through your computer's mic and speakers or by telephone. Your call-in number, access code, and audio pin are in the audio section of the control panel box on the right-hand side of your screen. All attendees have been muted to minimize background noise. If you have a question during the presentation, please type it into the questions box on the upper right-hand side of your screen. There will be a designated question and answer period at the end of the presentation. If you are experiencing any technical difficulties, please contact us through the questions box and we will try to troubleshoot the issue. With that, I'll pass it off to our first presenter, George Kushney.
Hello and welcome to today's webinar. We will be covering some of the results from a pollution prevention project that was funded under EPA's Source Reduction Assistance Grant Program. Specifically, we will be discussing a rinsing manual that was developed under this grant. I'm George Kushney. I'll be presenting much of the webinar today. Also with me is my longtime colleague, Dr. Paul Chalmer. The grant title, Pollution Prevention, Research, and Implementation for Michigan Metal Finishers. The grantee, National Center for Manufacturing Sciences. NCMS is based in Ann Arbor. Both Paul and I are NCMS contractors. The primary partner of NCMS was the National Association for Surface Finishing, NASF, and their educational arm, AESF Foundation. Together, these are the major trade group for the U.S. metal finishing sector. And throughout the project, well, among other activities, they were very instrumental in coordinating our efforts with Michigan plating shops and also national suppliers of P2 technology. Paul and I have both worked with these groups for going on 30 years now. The grant was expertly administered by today's host, EPA Region 5. And if you go to the next slide, please. I'm going to start by pointing out where you can locate additional project information and also access project deliverables. Olivia, please click on P2 project results. So we've gone over to a live internet browser. This is the Surface Technology Environmental Resource Center, STERC. It is an EPA Compliance Assistance Center, which is in the EPA OECA program. It was developed and is operated by NCMS. And as you can see from the logos on the page header, NASF and AESF Foundation are project partners of NCMS in this effort also. To get to the information concerning the grant, look at the left-hand menu, expand the library / articles, and go down to and click on EPA P2 project. Here you will find background information on the project as well as deliverables including P2 technology capsule reports. From this page you can also access the rinsing manual, the topic of today's webinar, and we'll do that in just a moment. Before we go there, I want to point out a broader aspect of the work that was performed under this grant. Two of the projects performed under this grant dealt with zinc-nickel electroplating. That would be the rinsing improvement project that we'll be talking about. And then the last bullet there, the demonstration of the Coventa zinc-nickel 3S technology, which is a bath maintenance technology for zinc-nickel electroplating. The zinc-nickel electroplating is a relatively new coating, especially as to compare to something like chromium electroplating. It has become very popular in the last decade or so in the automotive sector, where it's used for corrosion protection on steel parts. Because of its relative newness, there has been less P2 focus on this process. So for that reason, and also due to the fact that it has some unique pollution control issues, and I'll talk about those, zinc nickel electroplating was one of the focuses of this grant. So let's scroll down a little bit, please. And we're going to take a look at the rinsing manual, which can be accessed from this page. There are a number of locations on Stirk where you can find the rinsing manual. If you go to the home page, you'll find it. The manual starts out with an explanation of the 3 fundamentals of good rinsing. The appendices provide some more detail on each of these topics. The sections in between cover procedures for collecting data, organizing information, and making decisions. Just to give you a feel for the manual, let's take a look at one section. If you would go to Appendix A, please, Olivia, and click on that. And if you would go ahead and scroll down while I talk a little bit about it. What you're going to see here is an in-depth discussion of this topic, but you're also going to see a multitude of graphics and video. And these are instrumental in helping to understand the concepts that are presented here. There is no hard copy of the rinsing manual. It's just this online version. But this allows us to take advantage of multimedia and links to related resources. So for example, Olivia, if you could keep scrolling down to Figure 8. And would you start that? I don't know how well it'll show up for everyone, but here's some animation that explains how a particular P2 technology, a rinsing system, works. Now, if you scroll down to the bottom of this page, I believe, I wanted to point out. Okay, under direct drag out return, there's a link to Rinse Systems Calculator, and if you click on that, so this just shows another value of having the rinsing manual online. We can link over to the numerous calculators and tools that are available already on Stirk. And this particular one can be used by a shop to determine what advantages there are to different types of rinsing configurations. Well, you might ask why we need a rinsing manual. I don't think it takes an enormous amount of experience to identify potential improvements in an electroplating shop that are going to reduce pollution. Generally, these are very target-rich environments for us P2 types. However, keep in mind that nothing gets done unless the people with the purse strings give their approval. When presenting P2 recommendations to shop management, we must be able to answer 2 questions. What is it going to cost, and how much will it save? In order to answer these 2 questions, we need a structured approach that begins with data collection, considers all applicable alternatives, and logically develops potential solutions. I'm not going to walk you through the manual today, paragraph by paragraph. What I plan on doing is hopefully a bit more interesting. I'm going to talk about a particular application of the manual at a Michigan electroplating shop. And I'm hoping that today you can come away with an appreciation of how useful this manual can be. We could go back to the PowerPoint file. And if you'd advance to the next slide, please, Olivia. Before I jump into the technical discussion, I want to emphasize how important pollution prevention is to the metal finishing sector. The information here is from a previous NCMS study. During that study, NCMS surveyed hundreds of electroplating shops with the assistance of NASF. And using that survey data, we grouped the shops into 3 categories based on environmental performance, considering water use, hazardous sludge production, and energy use. The raw data were normalized by dollars of sales to take into account that there are various sizes of shops. We then ranked the shops and placed them into 3 categories. The best environmental performers, those shops with the least amount of water use per dollar of sales, the least amount of sludge generated per dollar of sales, and the least energy use per dollar of sales. And we identified a middle group and then the worst environmental performers in a bottom group. Then we looked at how much money these shops were spending on environmental operating costs, and the results are expressed there on the second column. And their units are dollars per $1 million of sales. And these results are just incredible. The best environmental performing companies are spending by far the least on meeting their environmental obligations. How does this happen? It's the implementation of pollution prevention. As you'll see from our presentation today, preventing pollution from rinse systems reduces water use, reduces waste treatment, reduces hazardous sludge generation, and it saves lots of money. I'd be remiss if I did not add that P2 is also a very important part of maintaining compliance within this sector. Reducing pollution at the plating line reduces the hydraulic loading and the pollutant mass loading on the waste treatment system, and we'll see that. In turn, this is going to lower the pollutant concentrations in the effluent, resulting in fewer violations. Please advance to the next slide. I'm assuming that not everyone on the call today has been in an electroplating shop. I hope you all get to do that at some point in your careers. These shops are extremely interesting, and you will find some of the nicest people there who care a lot about pollution prevention. So since we have a range of experience on the line, I'm going to start with some basic information so that we all have some understanding of the issues. This diagram shows the zinc-nickel electroplating line that we used as a guinea pig for applying the rinsing manual. A plating line is a series of tanks assembled in a particular sequence. In this case, the process starts on the left and ends up on the right. At the front end, there are cleaning steps. In the center, the electroplating operation itself, and that's followed on the right by post-plating steps. After each of these steps, there is a rinsing operation, and it is the rinse water that is responsible for the high environmental cost at metal finishing shops. This diagram's kind of plain and boring by itself, so let's look at the real thing. If you go to the next slide, please. This is the zinc-nickel electroplating line that diagram represented. It's referred to as an automated hoist line. It's automated, meaning that it's computer controlled. There's not a human operator running the racks through the various tanks in the process. The hoist, you can see, is that yellow piece of metal kind of in the center up in the top of the frame there. And that hoist holds 3 racks at a time, and each rack holds multiple automotive parts. And Olivia, would you please start video 1? In this clip, the parts have completed the plating cycle. They've been just removed from a drying tank at the far right of that diagram, and they're being transported to the front of the line. And there, the automotive parts will be removed, placed in crates and shipped to an auto manufacturer. This facility is a job shop, meaning that they don't own the parts that they plate. They plate parts for manufacturers and almost entirely, exclusively the auto industry. So now unplated parts will then be added onto the racks and the metal finishing process will be repeated. This line runs 5 to 6 days a week, 24 hours a day. Approximately 118 sets of those racks that we just looked at are processed in a 24-hour period. If you go on to the next slide, please. Well, I've told you that rinse water is the cause of high environmental cost. That's not completely accurate. More basic is something referred to as drag out, and that causes the need for the rinse water in the first place. In the rinsing manual, we devote an entire section and an appendix to drag out and ways to reduce it, and we glanced at that appendix just a few moments ago. Well, this next clip helps me to explain what I mean. And what you're going to see is the hoist lifting a set of racks out of the zinc nickel plating tank. And I want you to watch the zinc nickel liquid that's dripping from the parts in the racks. This is drag out, and it's the reason that rinse water is needed in the first place. So Olivia, I'm going to ask you to start video 2, and I'm going to ask you to pause it after about 10 seconds too, if you would. Please pause it right there. So the hoist has lifted the racks from the plating tank. And as you can see, the plating solution, again, this is the drag out, is draining off the parts in the racks. It's a pretty steady trickle. For this particular line, the hoist is programmed to suspend the rack over the plating tank for 8 seconds. Then it moves the racks to a rinse tank. The problem here is that the drag out has not completely dripped off the parts in the racks. Therefore, a lot of drag out is being transferred to the rinse tank. If you please continue the video clip. So it's sitting there now for 8 seconds. It's draining, it's draining, it's draining. It's still draining, but it's moving over to the rinse tank. It's now over the rinse tank, and you can see there's still a lot of dripping from that. Now, what is the cost of that drag out that we saw going into the rinse tank? Let's look at the next slide. Here's the annual cost of that solution that was ending up into the rinse tank. Each rack set, three racks per set, contributes 0.21 gallons of that viscous zinc nickel electroplating solution into the rinse tank. 118 loads per day, that works out to 25 gallons per day. Just the replacement chemical cost, almost $28,000 a year. The water, sewer, and waste treatment cost, almost $47,000 a year. And that waste treatment system is going to produce a RCRA F006 hazardous sludge, and that needs to be disposed of off-site at a cost of over $62,000. So that trickle that's going into the rinse tank is costing the shop over $137,000 a year. The next slide, please, Olivia. Let's talk about rinsing. So this plating line has 2-stage counterflow rinse systems after each chemical tank. Right now, we're looking at the rinses after the zinc nickel electroplating. The fresh water enters the rinse tank that we see in the center of the frame there. It's coming in through a pipe at the bottom of the tank, and it's being agitated. And it's coming in at about 3 or 4 gallons per minute. And then it is exiting the weirs on the left-hand side of that tank, which are kind of pinkish or orange colored. The water is flowing down a hollow wall and into the tank on the left. So this is called a two-stage counterflow rinse because we have 2 rinses next to each other. It's counterflow because the water is flowing from right to left, and the workflow is going from left to right. So the tank on the rinse tank on the left is going to get the most concentrated solution in it, and therefore it'll be the most contaminated one. The rinse on the right has to do the final rinsing, and it's going to be less concentrated. This is a very, very common rinsing configuration, and it's a pretty efficient one. You'll see this in most plating shops. The goal of rinsing is to get the parts as clean as possible using the least amount of water as possible before those parts go on to the next process tank. If you don't clean the parts sufficiently between process steps, you'll end up with poor plating results. The next slide, please, Olivia. For the next few slides, I'm going to be talking about conductivity. It is an easy and inexpensive way to measure the cleanliness of rinse water. Using devices such as these, you can generate a lot of very useful data in a matter of hours or a day's time. In the rinsing manual, we strongly recommend using conductivity when performing rinse tank surveys. You don't need a laboratory or a chemist to obtain some very valuable data. Next slide, please. So for example, conductivity measurements can be used to determine if your rinse water is too clean or overly contaminated. There are industry guidelines for acceptable limits. Those are shown in the left. And they're going to be different for each stage of the plating process. On the right, you see measurements that we took at the Michigan shop. And let's look at the table on the right under functional plating. The 2 rinse tanks that we just looked at, the more contaminated one has an average conductivity of 3,620 microsiemens per centimeter. And the cleaner one that was in the center of that frame, 356. So we take that, we compare that 356 number to the functional limit on the left table, which says 600. So in comparing those two, it looks as if this shop is using sufficiently clean water and getting the parts clean enough before they can go on to the next step. But these numbers don't really tell the whole story. The next slide, please. An important concept that we developed during the grant and we use in the rinsing manual is rinsing effectiveness, and it's defined here. We know that parts need to be as chemical-free as possible after rinsing, and we just looked at the recommended limits for conductivity in the last slide. Although they're helpful, they don't directly indicate how clean the parts are after rinsing. And this is important. The conductivity of the rinse tank water, which everyone has been paying attention to, is not as important as the conductivity of the water remaining on the parts after rinsing. I'll try to explain that better. So we've come up with this term rinsing effectiveness, and it's defined as the conductivity of rinse water on the parts after the rack has been removed from a rinse tank, divided by the conductivity of the water that's in the rinse tank. So how do we do that? Well, first we collect a sample of the drips of water that are coming off the rack and parts after it's been removed from a rinse tank. We measure conductivity, and this value is C1. If you go to the next slide, please, Olivia. And this shows how we used a device that we prepared or built just for this purpose. It's a piece of PVC pipe. We've taken a section out of the top and capped the ends, and we're holding it underneath of the rack as the water is dripping down after it's been rinsed. Next slide. And then we collect a sample of the water from the rinse tank that this rack just came out of. Measure conductivity, and that value is C2. And if you go to the next slide. So the rack had just been taken out of this rinse tank, and we grabbed a sample of that water, and that value, the conductivity of that is C2. And next slide, please. So then you calculate the rinsing effectiveness. It's the ratio C1 over C2. And I think most people would expect that C1 is equal to C2 and that the ratio is 1, because after all, the rack has just come out of a rinse tank. It has water on it, and that water came from the rinse tank, C2. But what we found during the course of the project is that this ratio of C1 over C2 is never 1. We found it to be between 1.5 to 5, where 5's the worst case. We want lower numbers for rinsing effectiveness. And we also determined what a good practice would be. And when we saw good rinsing practices, we were able to have that C1 over C2 ratio on the order of 1.5 to 3.0. And we'll have some more examples of that. We'll have a better understanding of it as I go forward. The next slide, please. One way of improving the cleanliness of the parts is to use more rinse water. That rinse that we were looking at uses about 3 or 4 gallons per minute of water. We could crank that up to 10 or 15 gallons a minute per water. But of course, that's going to create pollution, and it's going to be very, very expensive. The rinsing manual has a section on better ways to improve rinsing effectiveness, and here are some examples. First of all, you want to have complete mixing in the rinse tank. This can be achieved by tank design elements that prevent short-circuiting of the water, and we give some good examples of this in the manual. It can also be achieved by adding air agitation to the rinse water. In this case, air bubbles cause the rinse water to circulate in the rinse tank. And we're going to talk more about air agitation in just a bit. Second, you want to improve the removal of drag out from the parts. There's always a film of drag out that wants to stay on the parts and on the rack. And this is especially true with viscous solutions such as the zinc nickel electroplating solution. This is one of this kind of unique P2 challenges when it comes to zinc nickel plating. Well, here are a couple of examples of how to attack that drag out film. And there are a number of other methods that can be found in the manual. So first of all, spray rinses. They can be really effective at impinging on the surface of the parts and kind of washing off that drag out. We'll see that in just a moment. And then a double dip. And that's simply taking a tank out of a rinse tank and putting it back into the same rinse tank. The repeated in and out motion improves drag out removal. And it's not an expensive thing to do. If you go to the next slide, please. We're going to take a closer look here at air agitation. In this short video clip, you're going to see an example of both poor and good air agitation. Go ahead and please start video 3. So you can see on the tank on the left, very poorly agitated. If you look up toward the top of that tank, there's a complete dead zone. where water's not really being mixed at all. The tank on the right, I would consider that complete mixing. That's a good use of air agitation. The next slide, please. During this study, we measured the impact of air agitation using conductivity measurements and our C1/C2 rinse effectiveness formula. As you can see, air agitation has a measurable impact on rinsing effectiveness. By going from 0 to moderate agitation, the improvement is 14%. And going from 0 to good agitation, the improvement is 26%. And this improvement translates directly to water use. By adding good air agitation, you can use 26% less water and have the same level of part cleanliness. We didn't want to meet with shop management and suggest improvements like increasing air agitation, which costs money, without being able to provide the evidence that it's going to work and produce a savings. And this is the value of the manual. By following each of the steps, you're going to generate hard data that can be very persuasive. The next slide, please. This shop had a couple of spray rinses already in place when we started the project. And these spray rinses were made in-house, and they're pretty darn effective. The sprays come on automatically when a rack is lifted out of the rinse tank. They stay on for 6 seconds and automatically turn off. Olivia, if you'd go ahead and play video 4. There's pretty good velocity there of the sprays, and they're really impinging onto the parts and driving off that thin layer of drag out. So the next slide, please. Perfect. So spray effectiveness is different than rinsing effectiveness. Here, you want larger values. You want a small volume of spray water to remove as much drag out as possible. Our measurements at this shop indicated that the drips coming off the parts after spray rinsing, at C1 value, had a conductivity of 4 times greater than the water that was being sprayed, which was fresh water. If you'd advance to the next one, please. So the sprays came on for 6 seconds. There are 14 nozzles, 7 on each side of the tank, each one delivering 0.061 gallons per load. Again, 118 loads per day going through this plating line. Therefore, the spray, we're only using 101 gallons of fresh water and generating 101 gallons of wastewater. So the overall water use for this rinse system, that 2-stage counterflow rinse system, was over 4,000 gallons per day. Therefore, the sprays are only using 2% of the total water use, but they're doing nearly as much work as the immersion rinse. After we presented the cost and savings to shop management, they almost immediately added spray rinses to other rinse tanks. The next slide, please. There is an entire appendix in the manual devoted to ways of reducing drag out, and we looked at that. Here are 3 methods that you can find in the manual that were applicable to this shop. I'm going to talk about each of these and show some examples. Next slide, please. This shop had a rack maintenance issue, which is not uncommon in this sector. And what happens is that these racks, I believe these are aluminum racks, and they've been plastisol coated. That's a coating applied by an outside vendor. The racks are dipped into molten plastic, it dries, and it forms a coating on the outside. But what happens over time is that the plastisol coatings, they dry out from chemical exposure, they crack, and they can break away like you see here. And in this case, it was creating pockets between the plastisol coating and the rack. And so it was carrying additional chemical with it into the rinse tanks and even beyond rinsing. So the conductivity of rinse tank drag out for the racks with the damaged coatings were several times higher than for the other racks. And this is where we found that one value of 5 that we talked about earlier. And so after showing management how the poor rack coatings can affect drag out, water use, and their costs, the shop invested in recoating of racks. Again, this is the power of having data. Next slide, please. There are some of the new, beautifully recoated racks. The next slide, please. Sometimes people get used to seeing messes and they start to ignore them. My office is a good example. But when you document something like this and you bring it to the attention of management, it more than likely will get taken care of. And what we're looking at is the zinc nickel plating solution. We saw the drips coming off the racks as it's being transported to the rinse tank. Well, it's accumulated on the surface between the plating tank, which is on the left, and the rinse tank is on the right. And actually, this pool is kind of flowing toward the upper end of that surface and dripping down into the rinse tank and causing a need for the use of more rinse water. So this was another no-brainer. Almost as quickly as we pointed out the cost of this mess and made the recommendation, the shop solved the problem. The next slide, please. So what they've done is added a drain board, and that's this piece of PVC sheet that's been bolted down on an angle and covering that surface where the zinc nickel solution was pooling. Now when the dripping happens, it impinges on the PVC sheet and it's angled so that it goes, the drag out goes back into the zinc nickel tank, plating tank, where it belongs, and not on the surface and not dripping into the rinse tank. Okay, the next slide, please. We saw a similar clip earlier in the presentation. We're just at a different angle. And this is a rack that is going to be removed from the zinc nickel tank. It's going to be allowed to drain for 8 seconds and then moved to a rinse tank. Please start that video 5, I think. So we know that 8 seconds is not enough time to allow the drag out to drain off. But how long of a drain time is needed? We talked to management. They said it cost $10,000 to reprogram this hoist line. So we couldn't go to them and ask them if we could do trial and error experiments at that price to figure out an optimum drain time. So I turned to Dr. Paul Chalmer, my trusted colleague, who is much, much better at math than I, to come up with a recommendation on drain time that we could confidently take to management. So Olivia, please go on to the next slide, and Paul, would you explain what you did?
Sure thing. the first thing we wanted to do was see if there was any data in literature about whether anybody had made these measurements before in some sort of production setting. And there's not a whole lot out there, but in an EPA manual that had been published in the 80s, there was a picture reproduced, which had been published first by the old Beckman Instrument Company in the 1950s, which did have some sample plating solution and had the curves of what the drag out profile looked like versus time. What you're looking at is a curve, three curves, each one representing a different orientation of surfaces dripping over some test solution in a test tank. And the curve represents how much drag out is still remaining on the rack after a certain number of seconds. And as you can see, for the particular solution they were testing, there's quite a bit coming off even after, in the 30 to 40 second time frame. Typically, in the shop we were looking, and it's probably typical, they were letting about a 10-second drain time, between 8 and 12 seconds, depending on the position of, there's 4 racks that go into the plating tank, and the ones furthest away from the rinse tank take a little longer. But it's basically, we're looking at 8 to 12 seconds. So there were some curves. Now, you can't use just those curves because different plating solutions are going to have different viscosities. Run it at a different temperature, it'll have a different viscosity and so on. But this was a place to start. So next slide, Olivia, please. What we did in order to make the model was we looked at the curve and we said, boy, it looks like an exponential curve. So we tried to fit it with an exponential curve. The problem is that you don't get a whole lot of parameters to vary. If you want a simple exponential curve, you get a starting rate, you get a starting amount of volume up on the rack, and then you get a rate constant, which tells you how fast things are dripping off. And if you adjust the rate constant so it matches the beginning of the curve, then there's no way that's going to match the end of the curve. Like if you match between 0 and 10 seconds, the curve is way off and no amount of fiddling will get you to have it match between 40 and 60 seconds. The thing we discovered is that if you just take 2 exponentials, 2 starting volumes and 2 rate constants and add them together, just by fiddling with the 2 rate constants, you can get a really close match. And you can see that what you're looking at on the graph there is a superposition of the diagram that we saw in the literature, superposed with the best values that we could find of the plating constants, the rate constants. And you can see we could get a very close match between the surfaces, and the model was simple enough to allow us to make some calculations. Next slide, please. Now, with a little bit of mathematical scaling, is basically what we're doing. We found that by taking only 2 measurements in actual production situation, one measurement when the dripping is over the plating tank, knowing the start and end time when you from the time the rack has first totally emerged, you begin your sampling at some t equals like 2 seconds, and you keep your sampler under the rack as it's moving over the plating tank. When the rack has left the plating tank and it moves over to the rinse tank, another sampling person comes in, takes that sample for a couple of seconds before the rack drip falls into the tank. From those 2 measurements alone, you can compute that entire curve. You can get both rate constants and see what the curve should look like. So on the basis of this model, we created a rinse calculator, and I think I can get the screen if Olivia hands it over to me, and I can show you what you will see if you download the handout. There's some explanatory material up in the upper left-hand corner, and a document that explains in much greater detail what's going on as far as the theory and what we think is going on, why we think the model is valid. There's the URL for that. It's Appendix D of the RINS manual. The spreadsheet basically leaves nothing to the imagination. It's more complicated than the users of the spreadsheet need, but anybody who's interested can go through and see exactly how the math works. I won't spend a whole lot of time on that. I just want to draw attention to two particular features. One is we do present a graphical presentation of the curves that you calculate. First of all, I should mention, when you have your input data, that's the data that you enter into this box here. The volume collected over the plating tank in milliliters and the start and end times of that sampling. And this is some actual data that George and I took at this the shop we were in when we were doing these measurements. Same thing on the next line, the volume that was collected and the start and end time. So anytime you make a measurement, you can load it in here. And based on that, the model will show what the profile actually looks like. You'll find that at the start, if you take the difference between the start and end time values, that will actually agree with the volume that was collected. Same thing for the rinse time volumes. The upper curve shows the drag out left on the tank, just as the model curve did. The bottom curve is actually the sample that has dripped off the tank, so you can compare your measurements with what you actually collected. So both curves are giving the same information. Here's a chart of exactly what those numbers are, if you're curious. The other thing I wanted to point out is, in order to not baffle the people that you want to present this information to with information overload, we can boil things down to a single number. If you say, if I am going at a certain number of seconds now, and I want to have 10 extra seconds of plating time, put that in. This will compute for you exactly what the drag out reduction you would expect based on the model. And that's the number that you can present. Drag out reduction should turn into a measure of cost reduction for all of the consumables, things like treatment chemicals and other things that depend on the volume. Other environmental costs may not be sensitive, but anything that's sensitive to the actual physical amount of drag out will be contained in this percentage reduction. As you can see, a 10% increase in the time. In other words, instead of spending, looks like about 12 seconds over the plating tank for this one, if you spent 22 seconds over the plating tank, you could lower your cost by 24%. In the case of the company we were working with, it turned out that this is an expensive thing to do. We can show people the actual number. The barrier might be the fact that in these rack motions, certain things are in the plant operator's control and certain things are kind of hard-coded into it from the manufacturer. And it could be that the raising and lowering of a rack and that kind of timing is set by the manufacturer, because that's something you want to do as efficiently as possible to allow as little as possible collision time between all the other functions that the automated system has to perform. There are generally many racks going through the system simultaneously. If it turns out that that's the reason that the adjustment is so expensive to make, then customer demand would, if people are aware of the fact that they could save money if the controls were a little more flexible, it could well be that manufacturers would provide that as a feature, but first the customer has to be aware of it. So that's about all I wanted to say. And if anybody has any questions, be happy to answer them. George?
Thanks, Paul. If you go to the next slide, please, Livia. This slide summarizes the recommendations and the projected savings for the Michigan shop. We came up with 7 recommendations for them. Most of those were implemented before we even got finished with the project. And some they were still working on by the time the grant ended. But the projected savings, and I think these are very conservative numbers, reduced drag out by 25%. And if you look on the left-hand side, items 3, 6, and 7 would all affect drag out. And if you reduce the drag out by 25%, you're going to have the same reduction in wastewater treatment sludge, because it's the mass loading of pollutants that dictate how much sludge you're going to generate. Reduce water use by 30%. Many of the recommendations, I think 2 through 7, all would contribute to using less water at this facility. I don't have it on here, but the cost of implementation was somewhere around $25,000, including that reprogramming fee. And but the savings over $75,000 per year. And in addition to that, this is a much cleaner looking line. We had that mess cleaned up between the process tank and the rinse tank. The rinse water looks cleaner. It's doing a better job. The parts are cleaner as they're coming out of the rinse systems, and this all translates to improved work quality. The last slide, please, Liv. In summary, during the grant, which included multiple projects, most of which we didn't discuss today, we created a draft rinsing manual. We tested that draft out at a Michigan shop. We subsequently made some improvements to the manual. We finalized it, and now it's posted on STIRC for public access. And we hope that it becomes a useful tool for technical assistance providers, those people on the phone today, and also it sees internal use by plating shops. We're already getting the trade group to advertise the use of this manual. Purposely, it's not a printed document. It can be easily updated in the future, and NCMS is very open to your suggestions. I want to thank you very much for your attention this afternoon.
Thanks so much, George and Paul. We had a couple of questions come in throughout the presentation, and as a reminder to the attendees, in the remaining couple of minutes that we have, if you have any questions, please feel free to type them into the questions box, and we'll try to get to as many as we can. So the first question was related to video number 4, and it said, there is a lot of aerosolization in the sprays. Any issues there?
A lot of aerosol, was it?
Yeah, aerosolization.
From the rinse tank. It's not a very volatile solution, and the concentrations are very low in the rinse tanks themselves. So I wouldn't expect any issues with that. Now, the electroplating tank does have some air emissions, and they do have equipment in place for removing those and stripping those out.
Okay, this question may be related. Does spray rinse cause air pollution issues in the shop? I'm thinking of a spray rinse after chromiate tank causing hexavalent chromium emissions.
Some precautions might be necessary with certain chemistries, but in general, rinse tanks are not ventilated.
Okay. Our next question is, can some P2 practices at metal finishing operations qualify as green chemistry?
Certainly. This zinc nickel solution I mentioned, it's being used by the automotive industry for corrosion protection on steel parts. But it's more recently, it's been adopted by the aerospace industry as a substitute for cadmium plating, which is certainly a very toxic process. I'm not in love with zinc nickel because it presents some challenges, P2 challenges, but it certainly would be an improvement over CAD plating. There are other examples. There are non-cyanide solutions that are in place today that where there used to be zinc cyanide, copper cyanide solutions were very, very common 15 years ago, but today they're almost non-existent. Chromium 3, trivalent chromium, is being used as a substitute for hexavalent chromium, especially in decorative plating. But there are also some functional plating applications where you see that transition. So green chemistry, yes, it is a big part of pollution prevention.
Great. We had another question. Do you plan on doing a similar study with barrel plating?
Which type of plating?
Barrel?
Oh, with barrel plating. We had lined up a project during the grant to look at a rinse system that's designed specifically for barrels. And it was going to be one of our highlights of the grant, but unfortunately, the installation didn't finish up in time for us to look at it. And coincidentally, just 2 weeks ago, they got in touch with me and said, "We're ready." Well, of course, we've been finished with the project for close to a year, so there wasn't anything I could do about it. But I think, barrel plating definitely presents challenges. You have oftentimes several times more drag out with barrels than with rack plating. But there's a lot of work that's been done on redesigning barrels and injecting rinse water into the barrels themselves. And this new technology that you can find on a rinsing manual, that is also another way of helping out. So I wish we could, but we didn't have the time.
Okay. At any point, did you consider closed loop counterflow rinsing?
Not for this application. And again, this gets back to one of the challenges for zinc nickel electroplating. It's an ambient tank, so there's no evaporative losses from it. In fact, it tends to grow in volume during use. So the way a recovery rinse would work is that, say with chromium plating, for example, you have an elevated temperature. It might be operated at 135, 140 degrees, and you're going to evaporate 2 or 3 inches of liquid from that tank during the course of the day. And with recovery rinsing, you're able to use your rinse water to replace the evaporative losses and therefore not send that rinse water to waste treatment. And it's a marvelous way to reduce pollution.
Great. We have a couple of additional questions, but it looks like we've hit our 3 p.m. End time. We did have a question about whether or not the presentation will be available to be watched online. Christine, I'm not sure if you want to take that one.
Yes, we currently don't have a landing page for the recordings yet, so just those who have already registered for this webinar would receive a link to the recording.
Okay, great. Thanks so much. With that, we'll try to follow up over email with any other questions that we received through the chat box. And we want to thank you all for your time in attending this webinar, and have a great rest of your afternoon.